Thank you very much, Kosti. Thank you. I'd like to start by saying I apologize if there are some cuts in my talk today. I'm going to try and share my screen. I hope you can all see it properly. There have been some severe storms in Paris recently, so the internet may not be up to its usual standards, but if something cuts off, I'll start again the connection. In any case, thank you very much. Thank you to the organizers of this meeting for inviting me here today and giving me the opportunity to present to you a plenary lecture on the space exploration in search for habitable worlds in our solar system. And thank you for the kind words, Coustenis. And indeed, if we talk about habitable worlds, one of the places that I could highlight is, as you see here down at the bottom right, is the Observatoire de Meudon, where I work, near Paris, actually between Paris and Versailles. And you can see that represents a very nice example of one habitable and inhabited world. Inhabited worlds, so far, we have only discovered one in our solar system and as well as in the whole universe, and that's our own Earth. But when we talk about habitability, habitability is a different subject because it concerns the suitability for living in or on an object in our solar system or elsewhere. So planetary habitability is the measure, as we say, of a planet's natural or a natural satellite ability to develop and sustain life. And I usually, when I give a lecture, I ask people, what do they need to live? And they usually do start with the water that you see here, but also essential elements are required. That is generally what constitutes your body and what gives you the food that you use every day. But you also need some kind of energy, and a stable environment is something that we always need, and we tend to forget, because if we don't live in a stable environment, then we cannot have enough time for metabolism and life to develop and be sustained. So the definition of habitability is these 4 requirements, and this is what I'm going to be talking about in the rest of my talk, which is actually where do we find these conditions in the solar system and perhaps a little bit beyond. That's the extended regions of liquid water, conditions favorable for the assembly of the complex organic molecules, and energy sources to sustain this metabolism. So this is what you see here in this figure from Kevin Hand's work, very recent, on habitable worlds. So basically, let's see. Yes, so I'd like to start by saying that I think everybody's convinced by now that one of the most important goals, I would say, in space exploration is humanity's search for life, which is tightly connected actually to our better understanding of our own origins and the evolution of our own planet. And the requirements for life I just mentioned constitute what we call a habitable environment. And starting with liquid water, which is the main requirement, as you see here, the traditional habitable zone is the region that sits at a certain distance that you can see here from a star. In the middle here, you see our sun, and then you see stars with different masses here on the left, and the distance from a star for a given planet. And as I said, in the middle, you have the solar system. So starting with liquid water, the traditional habitable zone is the region where you can theoretically find a planet or a satellite with sufficient atmospheric pressure to maintain liquid water on its surface. And this region is what you see here as a blue strip for stars like our sun. And in the solar system, this area, you can see, fortunately, I'd say for us, has our Earth right in the middle of it. And so Earth is a habitable planet, but also the only inhabited planet known today. The search for other habitable worlds was first restricted to our close neighborhood, essentially Mars, which you see here on the right of this blue strip. And this is due to the fact that Mars may have been at some point in its life, as I'll discuss in a minute, conducive to life. Mars has then been a place of high relevance and interest for exploration, and still today, the planet we have visited the most, with about 20 missions at the very beginning of the space exploration, and about 50 or more missions attempted or landed or arrived today since the 60s. So on Earth, let me just mention that life leaves telltale signals in the atmosphere, essentially. Photosynthesis is ultimately responsible for the high oxygen levels and the thick ozone layer that we have here. Microbes emit methane and nitrous oxide in the atmosphere, and seaweeds and chloromethane gas. So these chemicals, when present in sufficient quantities, as I mentioned before, are indicators of life and known as atmospheric biomarkers. And that's what we try to detect usually. Detecting them in the atmosphere of an exoplanet one day should in theory be a means of discovering whether life exists on any alien worlds. While biomarkers have never been spotted in observations of an exoplanet because their signal is actually very faint today, and we are improving our means to look at it in the future, there is indeed a new generation of telescopes that are being planned today, such as the European Extremely Large Telescope or observations from space. Now, you may wonder about Venus, which sits on the other side of this blue strip. But Venus currently has a very dense atmosphere, 100 times that of the Earth. But as you can see in the characteristics here, the temperature varies from -40 to +460 degrees. And it's a very inhospitable world today with toxic clouds in the atmosphere. So we don't consider Venus to be a habitable world. But as I said, our exploration of the solar system makes us revise our models, as you also see in the rest of my talk, within even our solar system. So I'd like to actually start with Mars. Mars, 3.5 billion years ago, had a fairly dense atmosphere and a lot of water running on its surface, but it lost it, we think today, with substantial evidence due to the light gravity and lack of a general magnetic field that we can afford on our own planet. Some of the habitable conditions exist today on Mars, but early in its history, we think that Mars arguably looked much more like the Earth. Like it, most of its carbon dioxide was recycled in carbonate rocks. But without plate tectonics, and that's another strong feature that our planet has, Mars is unable to recycle rocks into carbon dioxide into the atmosphere, and therefore cannot maintain a strong greenhouse effect. So we're talking about a lack of greenhouse effect here. And it's therefore very cold there today. You have -60 degrees Celsius, and probably part of its atmosphere has been lost due to the solar wind and radiation in the absence of, as I said, a protection by a magnetic field. Mars still today, as you can see on this slide, has a fine atmosphere composed mainly of tiny amounts of carbon dioxide, but also some nitrogen, argon, as well as traces of oxygen and water. As for the average pressure on the surface of Mars, it's only, as you can see, 7 millibars. And these pressure and temperature conditions, therefore, do not allow for the presence of liquid water today on the surface of Mars. And water is present in the form of ice, which is condensed at the north and south poles of Mars, essentially. And in this region, there is indeed ice water below that of CO2 water, usually, that evaporates in the Martian summer and sends water vapor into the atmosphere. So we have a cycle there. But possibly there could be signs of past life on the planet Mars. And that remains an open question today. So this is the reason why Mars has been a strong attraction for exploration, and for good cause, as you can see here. Let me remove my, if I can, my video here. so you can see the slides a little bit better. So as I said before, there have been many missions that have gone there, but the Mars exploration until 2018, which is what I'm showing here, was a history with many failures. Actually, there were about 50% of all these missions that had failed to get to their target. And many international stakeholders had attempted it. You can see here all this family of missions. Flybys and images of the surface were first acquired by missions like the Russian Mars 1 to 5, or the American Mariners 4 to 9 in the 60s. The Viking missions, also in the 70s, very early brought orbiters and landers with great success, but that was followed by a long absence of exploration, except for the Phobos orbiter, until the mid-90s with Mars Pathfinder and Mars Global Surveyors. And this was due to the fact that the Viking missions were sent there to find life, and they failed to do so. But the early years of the 21st century marked also the arrival of Mars Odyssey, followed by ESA's Mars Express and NASA's rovers in 2003, and Mars Reconnaissance Orbiter and the Phoenix missions. So in the past decade, the exploration has accelerated with more successes like MSL and MAVEN, but also EXOMARS TGO and InSight. So just to show here that there are new indications, very recent indications of past water on Mars from surface features, as you can see here, that from MSL Curiosity with layer deposits in Yellowknife Bay, and also from Omega and on Mars Express for the discovery of clays in the all-terrains of Mars. So we have some indications of the presence of abundant liquid water in the early history of Mars. But if it existed, it must be searched for in very old terrains in the first gigayear of Martian evolution. And this is one strong constraint for future missions. So this artist's concept depicts the early Martian environment here on the right, as we believe it to be, with lots of liquid water and a thicker atmosphere, versus the frigid, inhospitable environment seen at Mars today, which is what you see here on the left. But as we saw, Mars has features like dry riverbeds and minerals that only form with liquid water and indicate that long ago, it had a thick atmosphere that retained enough heat for liquid water to flow on its surface, and hence perhaps may have witnessed actually the emergence of life. So it appears that Mars has lost much of its oceans and its atmosphere over billions of years, and it transformed its climate from one that might have supported life into the desiccated and frozen environment of today. And this comes from the results from missions, like I said, such as Mars Express, ExoMars TGO, MAVEN, and Curiosity, and all the way back to the Viking missions of 1976. But the family of missions to Mars is going on. It's growing even more recently, with more missions now in place since just this past year, bringing it up to something close to 50 missions by 9 different nations since the 60s that you can see on this slide. And all of these missions search for signs of extant or extinct life on Mars. But the next steps will necessarily be to go deeper, like I said, on very old terrains on Mars and do a more thorough exploration and eventually bring back pieces of Mars to Earth. So with such goals, 3 new spacecraft were launched, and I'm sure you didn't miss the news that also arrived at Mars just these past couple of months and are highlighted here in the yellow ovals that you see here up on the right. And these 3 missions that arrived this February 2021 to Mars to complete the current fleet, bringing it up to 11 missions in operation on site today, where the United Arab Emirates' first interplanetary HOPE probe, Al-Amal, which is orbiting Mars to study its atmosphere and climate, among other, and looking for connections between today's Martian weather and the ancient climate of the red planet. Then you have China's Tianwen-1 Mars mission, which consists of an orbiter, a deployable camera, a lander, and a rover. And the goal here is to assess the planet's environment while also searching for evidence of both current and past life. And finally, the NASA Mars 2020 mission with the Perseverance rover, which will study the Martian surface at Jezero crater and will drill and collect core samples of Martian rock and soil and store them in sealed tubes to pick up by a future mission that would ferry them back to Earth for detailed analysis. And this is just a slide showing China's robotic spacecraft Tianwen-1, which, like I said, consists of an orbiter, a deployable camera, lander, and the Zhurong rover, which actually landed and deployed on May 19, 2021 on the surface of Mars. That's its first try. So congratulations to our Chinese colleagues, and transmitted its first colored images. So visually and technically, Zhurong is very similar to NASA's Spirit rover. So we have all of these fantastic missions and opportunities to study the surface of Mars. And the front view here shows the flat landscape of Utopia Planitia. But indeed, another successful mission that you see here is Mars 2020 with a Perseverance rover that has a strong international collaboration. Actually, my own laboratory, LESIA at Meudon, built parts of the camera that sits on Perseverance, which has many scientific goals concerning the geology, astrobiology goals to determine whether an area of interest was suitable for life. But we'll do also, as I mentioned, sample caching and prepare also with test technologies for human exploration someday. And this is really an amazing mission. You can see here the payload, but also this small helicopter that you can see taking off on this slide and landing a little bit further on the surface of Mars, which tells us that it's very high level technology because the Martian atmosphere is very thin, as I mentioned before, 7 millibar. But we can fly things now on Mars besides deploying rovers. So a fantastic mission here. But I would like to take a minute to talk about the next missions to Mars, which are components of the EXOMARS project that ESA and Roscosmos have together. EXOMARS for exobiology on Mars is an astrobiology program by the European Space Agency and Roscosmos. And since its inception, it has gone through several phases, but together today, these two missions have as a goal to search for signs of past life on Mars, investigate how the Martian water and geochemical environment varies, and investigate atmospheric trace gases and their sources. And by doing so, demonstrate the technologies, like I said, for a future Mars sample return mission. And you can see here the two elements. The first is the Trace Gas Orbiter, which launched in 2016. And the second one, comprising a rover and a surface platform, is planned now for 2022. And together, they'll address the question of whether life has ever existed on Mars. And you can see here some of the results from EXOMARS TGO, which were published 3 years ago. And you can see all the instruments on board working together, ACS and NOMAD, for instance, looking for methane. ACS showing the presence of hydrogen chloride, which may mean that there was some magmatic activity at some point. NOMAD and ACS measurements looking at the vertical distribution of dust and water vapor and showing water loss on Mars. And FRIENDS map of the distribution of minerals or water-rich ice and looking at subsurface hydrogen. That indicates that on Mars you have water present in very many different forms. And I invite you to look at Science Advances and other publications, very recent publications of this year, to look more thoroughly on some of these results. One of them I just wanted to highlight is the search for methane on Mars, which has been detected by some instruments on Curiosity and Mars Express. That's a somewhat surprising result because the atmosphere of Mars is oxidizing. But at the same time, TGO has looked for Mars and hasn't seen it today. So the presence of methane on Mars is to be close to the ground if it exists and remains to be confirmed and explained. But this could be linked, if it's not obviously a metabolism of living organisms as on Earth, to volcanic or hydrothermal activity. And the fact that we don't see it could be explained by heterogeneous chemistry that destroys it at higher levels. I wanted also to mention as a spectroscopist how difficult it is to interpret the measurements made by the various instruments in the presence of other atmospheric gases at the same place. So the question remains of methane on Mars. But one thing that is for certain is that both MEX, EXOMARS, and every other instrument on the surface of Mars has been showing the presence of water in the past, but also found evidence for important chemical interaction, has looked at characterizing the distribution of ozone and other components, and has been working in general on enhancing our understanding of Mars. So we're looking very much forward next year for the launch in probably in September 2022 by ESA and Roscosmos. The mission that will deliver 2 new science elements on the Martian surface, a lander instrumented to conduct environment and geophysics measurements named Kazajok, and a rover, 310 kilograms of rover, tasked to conduct a search for signs of life. And it's called Rosalind Franklin. And this rover has the specificity of going very deep down at 2 meters, drilling at 2 meters in a place that we call Oxyaplanum, and that you can see here on this video. Oxyaplanum is the site that we selected because it contains some of the largest exposures of clay-bearing rocks on Mars. And the age of this region, as I said before, we need something very old, was calculated to be from 3.6 billion years old to 4 billion years old. So we're talking about a very old terrain. And the site is iron magnesium rich clays, indicated that water once played a role here. And it sits in an area of valley systems with the exposed rocks exhibiting different kinds of compositions, indicating a variety of deposition and wetting environments. So all of this hypothesized to have occurred from either fluvial deposits or by volcanic activity during the Amazonian period on Mars. And erosion is supposed to have also occurred here. So this is the site we're going to be looking at with EXOMARS. And some people consider Mars, I'd like to say, only in the light of a sort of colonialism, you know, for human exploration, or even just exploiting it for our own purposes. But there is a lot more to it, a lot more to the exploration of Mars. And in any event, Mars deserves to be first thoroughly robotically explored. And in particular, there is an additional step to take before anything else happens, and that is to bring little pieces of Mars back to Earth. And this is what we are going to achieve with the future Mars exploration with a project called Mars Sample Return that you can see here, which is an exciting and a very ambitious project based on a substantial international collaboration, particularly between ESA and NASA, to bring Mars species back to Earth, and with very well organized steps that you can see here with the Mars 2020 rover that I just mentioned, a sample retrieval lander, which will deliver to Mars a sample fetch rover to retrieve the samples that I mentioned before were going to be acquired by Mars 2020, via a sample transfer arm that will load the samples into a container, and the Mars Ascent vehicle to launch the container into Mars orbit, where it would be captured by the Earth Return Orbiter, which is made by ESA, and will deliver the samples to Earth by the Earth entry vehicle. So you can see there are a lot of elements in this mission, and it has to be working perfectly. So it takes some time to put in place, but we're at the first step now with Mars 2020. And the last step will be the delivery of the samples in a Martian returned sample handling facility, which is a very important facility that would serve to receive and quarantine samples sometime in the very beginning of the next decade. We're talking 2031 currently. And this element would also be used for assessing hazards and providing the opportunities for the international scientific community to conduct sample analysis. So this international future exploration would bring us exceptional new understanding of the Martian environment, as long as we obviously take care to not contaminate the alien environment or our own Earth. And for this, I would like to make a pitch for my other function, which is chairing the COSPAR panel on planetary protection, which is there to develop, maintain, and promote the COSPAR policy, which is actually just these two sentences here: to conduct scientific investigations of possible extraterrestrial life forms, precursors, and remnants by taking care to not jeopardize them and not to contaminate the place that we're looking at. And in addition, the Earth must be protected from the potential hazard posed by extraterrestrial material carried by the return spacecraft and the samples that we bring back mostly. So we must take care not to lose sight of that statement when we explore. So basically, ESA has been going to Mars and back for quite a few years now. And I'll let you enjoy this video here that discusses the programs in Europe. So you see that we have a lot to look forward as concerns Mars, but now I want to go back to the habitable zone, where we have now indications of needing to remodel the habitable zone, because in recent years we have found liquid water oceans underneath the surfaces of some of the moons of the giant planets. And I'm sure you haven't missed the new discoveries around the icy satellites of Jupiter and Saturn, with first some indications around Europa, and then also the geysers that were observed around Enceladus for the Saturnian system. So the exploration of our solar system now for habitable worlds has been extended to the outskirts of our solar system. And just to say that I would like to say that many years ago, actually now 2009, more than 10 years ago, we did a paper on the habitats that are possibly existing in our solar system. And we have different classes there, where class 1 and 2 are the habitats that resemble our Earth or Mars or Venus. But now in the class 3 and 4 habitats, we have planetary bodies where subsurface water oceans may exist. In class 3, they interact directly with the silicate-rich core. That's the case of Europa and Enceladus, for instance. And class 4 is habitats that have liquid water layers sandwiched between two ice layers, or in some cases, liquids above ice. And this is what we were actually finding in our solar system with missions like Galileo around Jupiter and Cassini-Huygens around Saturn. And you can see here this different icy moons that I'll be discussing, and the internal structure that shows those sorts of hydrospheres that exist there with quite some liquid water to exhibit. And I'll start with Jupiter, that is being explored, as you know, by the Juno mission, and which has 3 large icy moons to explore. Ganymede, the largest satellite in our solar system, that has a deep ocean inside a hydrosphere between 2 ice layers, but also an internal dynamo and an induced magnetic field, and very rich crater morphologies. You have Callisto that we don't know very well even today. We still don't know if it is differentiated inside, but it still presents a strong testimony to very early ages of our solar system. And Europa, which has, we think, a very deep ocean and actually close to the surface. And we think it's an active world and the best example for liquid environments in contact with silicates. All of these satellites sit at certain distances from Jupiter. Obviously, I don't consider Io to be a habitable world. It's too close. It has iron melting on its surface and more than 400 volcanoes. And obviously, the closer a moon is to Jupiter, the hotter its interior, but also the more it suffers from radiation effects, which is actually a case for Europa. And Europa is one of the first satellites that gave us indications of a possible liquid water ocean underneath its surface, because what we see on the surface is actually images that resemble what we have on the Antarctic Ocean of Earth, with pieces of ice floating on a frozen sea, which would have been liquid in the past and reorganizing themselves in bits and pieces like you see here. But Europa also shows some evidence for plumes that were detected not very long ago and were confirmed by HST data very recently. And you can see this very strange surface that geologists love to look at to find indications of what could be hiding within the interior. But also it's important to say that surface oceans could be in contact with silicates on the seafloor. And this opens the question of where the building blocks for life could come from. By assuming the organic material necessary to start life is supplied by impact of meteorites, as you see here at the bottom right, and comets, and by precipitation of interplanetary dust, for instance, this material impacting on the surface has to find its way into the subsurface oceans. And this is the issue here. And it has to reach meaningful concentrations in some small compartment of the ocean. And this is hard to imagine in a connected body of water as large as a planet-wide subsurface ocean. But however, we can keep in mind that synthesis of organic material by either Fischer-Tropsch reactions, which convert carbon monoxide and hydrogen into hydrocarbons, or catalytic cycles are possible under the conditions that we have there, which is the high pressure, high temperature conditions that we see in these deep sea vents. So such conditions on Earth reduce radicals in hot liquid and can provide also the energy for the sustainability of some living organisms. So we don't know exactly what's happening on Europa, but it's a large satellite that retains heat. On the other hand, is it a steady environment, and how can we compensate for the radiation problems there? Another important satellite, I mentioned this before, is Ganymede. Very important to characterize the local environment of Ganymede, where we have evidence of an induced magnetic field created through the interaction between the Jovian magnetic field sweeping past and a conducting layer. And this is what we think constitutes the subsurface ocean. And it's Ganymede is the only actually known planetary moon to have its own internal driven dipole magnetic field with a similar strength to Mercury's actually dipole field, a few hundred nanotesla at the surface. So this is a large dipole field which masks to some extent the induced field, which is embedded because Ganymede is embedded in the rotating variable background field of Jupiter's magnetosphere. And we have a mini magnetosphere there within a magnetosphere. but we don't know all its characteristics. And so we need to decipher and distinguish all these different components and the interaction of Ganymede's mini magnetosphere with Jupiter. And at the same time, on Ganymede, you have an old dark terrain that covers 1/3 of the surface. And the other 2/3 have been resurfaced to form light terrain. So a lot of information also on Ganymede's surface and indications of this liquid water ocean, where the question now is, can it be habitable if it's sandwiched between two ice layers, as you see here? So also on Ganymede, some very recent images of the auroras that have been observed on the moon and are controlled by Ganymede's magnetic fields that I just mentioned. And you see the two auroral ovals that can be seen over the northern and the southern mid-latitudes. Very nice images from the Hubble Space Telescope. So I just wanted to mention also briefly the JUICE mission, which is an ESA-led mission to focus on the exploration of the Jupiter system with two overarching themes that you see here: the emergence of habitable worlds around gas giants and a thorough investigation of the Jupiter system as an archetype for gas giants. You can have a lot more of the information regarding this mission and all its topics that it's going to really investigate the Jupiter system from the interior all the way out to the atmosphere and plasma environment, habitability. The current considerations for the project are shown here, where the main contractor is Airbus. And you can see all the characteristics of the project at the current time, with the solar arrays that are going to take us there and are going to be 60 to 70 square meter big. But also here are the important elements of this mission, which is the interplanetary transfer, which is foreseen on an Ariane 5 from Kourou. And so next year, we're going to fly in September 2022 and do the interplanetary transfer, and then the orbit insertion and 2 Europa flybys that you can see here are going to be very important to find more information. On the satellite, here is the payload that we have on this mission. You can see we have remote sensing suites, geophysical experiments, and a lot of packages for particles and fields investigations. And all of this is going to help us to characterize the liquid water ocean underneath both Ganymede and Europa, and look at the internal structure of Callisto. So obviously I cannot describe the whole mission here. I just wanted to say that the flybys we're going to make of Europa and Callisto will give us a lot of information that is also going to help another mission to the Jupiter system, which is the Europa Clipper mission here, which will launch in 2024. NASA is preparing these very thoroughly in the coming months, and the two missions could actually arrive at the same time and do synergistic observations. So this is for Jupiter, and very quickly, I just like to finish with saying a few words about the Saturnian system, where we had the Cassini mission that thoroughly described for us the whole satellite system around Saturn with many surprises. And I just wanted to say that this has been a fantastic mission with 12 instruments on the orbiter and 6 instruments on the probe. So everybody knows about this mission that made a lot of discoveries, and in particular revealed to us 2 of its satellites, Enceladus with the geysers that sprout out liquid water, water vapor from the liquid water ocean out in the atmosphere, and Titan, which is the equivalent of a frozen Earth, but has so many different features on its surface and in its atmosphere resembling our own planet. So the discoveries that we have for the icy satellites from the Cassini mission were just exceptional. And they have demonstrated the need to go there back at some point. And we obviously want to go and explore further, for instance, the liquid water ocean underneath Enceladus, and also the organic material being ejected from its plumes, where we have salt, organics, we see nanograin dust, hydrogen, and ammonia. and also very recently some evidence for hydrothermal chemistry and discovery of a strong thermal anomaly on Enceladus. And all of this is very easily reachable because it's coming out from the geysers to space. And so we can very well look at all of that by a mission that just scoops through the atmosphere. And obviously, we all know about Titan. I just wanted to finish here by saying that Titan has been a demonstrator of how much the exploration of our solar system for habitats is important, because we have realized that looking at a planet that has seasons so much larger than our own, with 7.5 years per season, is important, because the dramatic changes both in temperature and in atmosphere at the poles is an indicator of how our own planet can change in the future, even if we have different constants in time. So very important to go back to Titan, look at its surface, that it has all these different features that we find also on Earth, especially from the Huygens probe, where you can see here a picture of its landscape with the channels, the hills, the dried lakes, and all of these constituents that highlight the interest of Titan in respect of being a unique body in the solar system, but also in comparison to what it can teach us about our own planet. And I'd like to point people to recent papers describing one of the main features on Titan, which is the methane-rich lakes, but also the presence of constituents, organic constituents on the surface seen by the Huygens probe. And finally, indications, strong indications of the presence of a liquid water ocean underneath its surface. So we're all convinced that Titan and Enceladus constitute habitats, potential astrobiological objects in our solar system that need to be explored in the future very thoroughly, because we have oceans in the solar system underneath the surfaces that contain a lot more liquid water than even on our own Earth, 10 times more, orders of magnitude more liquid water on some of these icy moons that you can see here, Enceladus, Europa, Ganymede, and Titan. And so the end of the Cassini-Huygens mission in 2017 doesn't mean the end of exploration, because in the future, we have some missions coming up, and in particular, the Dragonfly mission, which is a mission that will send a rotorcraft lander to the surface of Titan in the mid-2030s, and we look for prebiotic chemistry, habitability, and potential chemical biosignatures from both water-based life as we know it, in potential cryovolcanic flows, but also from protection life, but not as we know it, that might use liquid hydrocarbons as a solvent. So that's it. And for Enceladus also, we have future missions coming up. The ESA fleet is ready to explore our whole solar system with its missions in the future, in the coming years. So stay tuned, because the ESA's Voyage 2015 new scheme will focus also among the 3 themes that were selected on the moons of the giant solar system planets, before going to exoplanets and new physical probes. So icy moons are very important in the future. I invite you all to look at the ESA's website for more information, and I thank you for your attention.
Thank you very much, Athena. I think that in the chat we have some questions that I expressed. Do you want to, for example, start with the question of Paco Colomer?
I don't see, should I stop sharing my screen? Okay.
Not necessarily. Yeah. It's like, okay. But in the chat, you have the questions.
Yeah. Okay, humankind-wise use of outer space are the countries and companies in the context of space belongs to everybody. Yes, well, the COSPAR policy, dear Paco, doesn't say that you cannot explore. Actually, there is not one single place in our solar system that the policy forbids from exploring. The idea is to explore with a certain care, both for what you bring back, but also essentially for not disturbing the scientific exploration that you perform on site. If you bring life from Earth, if you haven't sterilized your spacecraft or your instruments and you bring life to Mars, then you'll detect it for sure, but it's not going to be Martian life. Now, for the exploitation, we're also looking into that. If you're talking about ISRUs, the in situ resources utilization, that's another very important subject that we're looking at, because you cannot go and start mining on other objects without rules, regulations, agreements between the different countries. And I invite everybody to look at the new center in Europe, which is in Luxembourg. It's called ESRIC. They're going to be looking at how can we better use some of the resources that are, for instance, found on the moon or Mars, but without destroying the evidence for chemical evolution, for water presence, and so on. So, Cassini, you want me to go through the questions?
So the next question here, they are on the chat. So the next is from Evanthea Hadjiminaoglu.
I think I responded to that, but we can do a little bit more conversation if you want, because ethical considerations are not part of the COSPAR policy. The COSPAR policy is about science. Ethical considerations obviously have to be taken into account, Evanthea, but this is something that has to go through also discussions with the United Nations and space law and things like that. So I'm with you on that question. I don't know about the future. So the Pride experiment, yes.
Oh, there is a question from Malavelias that I see here. I don't know if
Yeah.
About water and carbon-based chemistry. What about alternatives in our solar system? Do you want to comment on that?
Yes, absolutely. Because so Grigori, I said at the beginning that I'm looking at habitable conditions as sort of like extrapolated from what we have on Earth, but obviously that's a very egocentric way of looking at things. Now, on Titan, for instance, there have been discussions about methanogenesis. As you mentioned, liquid ammonia could play a role. I actually had a slide from my good friend Carl Sagan, where you see an alien arriving on Earth and romping around and calling for ammonia, because that's how that alien life lives. And indeed, I think by exploring the solar system, we'll learn more and more about what kinds of different lives we could have. But for the purpose of the current exploration, we have to go with what we have on our own planet.
We'll go. There are many questions, and the next one is from Caballero. Could you briefly comment on the importance of asteroid exploration?
Yeah.
You said, I don't know if you see it, even if it's not habitable. Would it be important?
Yes, absolutely. And I only mentioned very briefly when discussing Europa, for instance, the fact that you have comets and asteroids and all of these impacts that have been considered for quite some time as having brought some of the essential elements that made our planet habitable and inhabited. But of course, their exploration is extremely important, and we're finding new things. In my laboratory in Lesia, we have many experts on asteroids and meteorites and comets, and every day they find new results, and whether they fit into the general scheme that's what brought life constituents to Earth or not is still, I think, in debate. But they certainly contribute. And in the case of Europa, for instance, we need this kind of impacts to bring oxidants and organics on the surface that can then be distributed further inside. But the exploration of asteroids in the solar system, you may have heard of Comet Interceptor, which is a small class mission of ESA that is going to also fly with the Ariel mission in the late 2020s. And of course, the Rosetta mission and Philae have brought us a lot of information that we're still investigated. So absolutely, it's very important to look also at asteroids and meteorites and comets.
One or two questions more. There is a question from Kostas Markakis. Would like to ask the timescales involved in the Mars terraforming process. You want to comment on that?
Yeah, well, we don't know. I mean, frankly, how much time it's going to take to transform a 7 millibar very cold atmosphere to an atmosphere that can be breathable on one hand, and how much time it would take to also get liquid water back on the surface as we might need it, is an object so far that has been looked at by institutes in the United States. I know JPL has done some studies on that, and other NASA institutes are looking at it, but has also been a lot in science fiction, you know, so far. I think it's a very complicated issue. If we're talking about just one location on Mars that we make like in sort of a biosphere, then that could be achieved much faster than if we want to transform the whole of Mars. So I don't have a specific answer for that, dear Konstantinos, but we're looking forward to see what the studies come up with.
And now two questions. The one from Manolis Georgoulis, and this is, how do you think Mars lost its magnetic field that may have led to atmospheric loss? And also another question, how strong was the magnetic field on Mars? That was from Noah. Do you have any idea?
Probably people on this conference know more about this than me, but the idea came from actually the measurements that the MAVEN mission has done around Mars, and it's very complicated to know exactly how big the magnetic field was on Mars previously, but the calculations that the MAVEN mission did recently indicate a loss of this atmosphere being stripped away by the solar wind. So they have done the calculations. I don't have the paper exactly in mind right now to tell you what was the time scale for that, but it has stripped away a huge part of the Martian atmosphere. I know that over billions of years probably, but it's accelerating, and that's the one result that is very worrisome at this time. The MAVEN results are showing that the loss of the Martian atmosphere is continuing and accelerating at this time. So there may come a time when Mars has absolutely no atmosphere left. And I don't know how big the magnetic field was previously on Mars, but it wasn't strong enough to hold on to the atmosphere at those distances from the sun.
And we have a comment from Anesina Solomonidou. She thanks you for the presentation. We definitely need to go back to Titan and Enceladus and explore the icy moons of the gas giants like Triton.
Yeah, Triton is out in the icy giants, and obviously it's an important new exploration theme that we have. I'd like to mention that the Decadal Planetary Survey, NASA's Decadal Planetary Survey, is taking place currently as we speak. And one of the themes that may emerge there would be exploration of the ice giants. It's very important and timely that we do this very quickly now, because the windows for the launch that we could get us to Uranus and Neptune is closing up fast. And ESA and NASA are discussing about a common endeavor to take probes out there and study our ice giants. And obviously there are satellites, and Triton is of high interest because of its geysers.